In this video, we're going to look at using Fourier transforms to solve a problem rather than filtering data. We've got some problem that we can write down as a differential equation, and solving this differential equation in the time domain is hard because we've got a dragon in the way. So what we're going to do is take a transform of our problem, solve the transform problem, which is going to be super easy and relaxing, to get a solution in the Fourier domain, and then transform back again. The first problem I'd like to consider is a simple circuit. In this case, we have a driving voltage, V in, a resistance, and a capacitor, and we want to know, for a given input voltage, V in t, some function of time, what's the voltage across the capacitor? Well, let's solve this circuit using the laws that we know for circuits. The voltage across the resistor is VR equal to IR, where I is the current in the circuit, but we don't know the current. The current, though, across the capacitor, we know is given by the capacitance multiplied by the rate of change of the voltage across the capacitor. So this gives us that the voltage across the resistor is R times C times the rate of change of the voltage on the capacitor, substituting this into here. And then if we use Kirchhoff's law to go all the way around the circuit, we know that the voltage across the capacitor and the voltage across the resistor added together must be equal to the input voltage. So now we have a differential equation for the voltage across the capacitor that depends on the input voltage. And this is the equation we want to solve. So let's do the solution for an input voltage of a delta function. So V in t is a delta function of t. That means a solution of this equation will be the impulse response of the circuit. So here's our equation now with delta t. This is hard to solve with delta t here as a driving force. We don't really know how to deal with this in the time domain so well. So let's use Fourier methods. Well, taking the Fourier transform of this equation, the derivative here goes away and we just multiply by I omega. The voltage across the capacitor here, this becomes the Fourier transform of the voltage across the capacitor. Likewise here, and the transform of delta t becomes 1. Rearranging, we find an equation for the Fourier transformed voltage across the capacitor. It looks like this. I'm going to rearrange that a little, taking out a factor of 1 on RC to have it in this form. And the reason for that is, if you look up the table of Fourier transform pairs, this is one of them, where we have a 1, an I omega, and then some constant here. So we can use this in the next step. But I'll point out that this term here is the transfer function. This is the transfer function that takes your input voltage to the output voltage. And taking the inverse transform, we find that the output voltage across the capacitor can be represented like this, where this h of t is a unit step function. So that's something that is 0 for negative time and becomes 1 at time equal to 0, and then it's 1 for all times after that, and a decaying exponential. And this whole thing together is now the impulse response. It's the Fourier transform of the transfer function. So it looks like this. 0, and then suddenly it jumps up and then decays down. So here we've used the Fourier transform to solve a differential equation and the inverse transform to get back to the time domain solution. So this now is the voltage across the capacitor for a delta function input here. So now we know the response of our capacitor, the voltage across our capacitor, to this delta function. What's it useful for? Well, it's really useful because now we can write down the voltage across the capacitor, Vc of t, as a convolution of the impulse response with any arbitrary driving voltage in time. So this is now a general time equation for the solution of our differential equation, written in terms of the impulse response convolved with our driving voltage. In the frequency domain, then it's just the Fourier transform of the output is equal to the product of the transfer function and the Fourier transform of the input. So let's take an example. Let's imagine our driving voltage now is a square wave with some width tau. So the output voltage, the voltage across the capacitor, we can write as g of t, which is given by this equation here, convolved with our square wave. Or in the frequency domain, it would be the Fourier transform of g of t, which is g of omega, multiplied by the Fourier transform of our input. That's the Fourier transform of the square wave, which would be a sinc function. We end up with this factor of tau at the front as well from the Fourier transform of this square wave. So using this time domain expression, I'll show you an example where we have tau equal to 2 seconds, that should be, and 1 on RC equal to 2 seconds to the minus 1. And this is an animation of our situation. So here is our square wave drive, and this is the impulse response in blue. And as the drive hits the capacitor, we see the capacitor charging up, drive turns off, and the capacitor decays. So that's that. Now you can also derive these curves in piecewise form from here to here, the positive sloping part and the negative sloping part, because you know how capacitors charge up and discharge. If you just turn a voltage on and watch the capacitor charge up, you can write down an equation for this part of the curve, and then when you turn off the voltage, you can measure the rate at which the capacitor discharges. And so this is the charge up and this is the charge down.